Today we are going to focus on the programming aspects of discrete event simulation. We are used to looking at the mathematical models before, and we also talked about what discrete event simulation is. So there are several software tools available that can help us realize models, write models for discrete event simulation, and then based on that do performance evaluation and so on. This is a tool that goes back to almost 20 years, and it might be old, but I think it's still useful. It's basically a collection of C routines, and therefore those who know C programming or C++ programming can start quite easily from this. There are other more sophisticated tools like NS2 and NS3 more recently, things like Omnet++ and so on. Those are particularly designed for network simulators, for network simulation, and there are tools for other domains too. But the reason Yaxim I find particularly useful is it's very generic. It gives you very bare bones set of functions that you can use, and with the help of that you can construct fairly reasonably good size simulations. The advantage is you can decide the level of abstraction that you want, right? So in the case of NS2, NS3, the abstractions are not that easy. You have TCP layer, IP layer, and so on. With Yaxim, you can just exactly decide what part of the system you want to abstract, and then build the model for that, and then realize that with the help of this C code. Okay. So we will go through this some of the details of this Yaxim manual. It's fairly large manual, about 60 pages or so, but most of it is self-understandable. You can read once and kind of figure out things, but I wanted to highlight some of the main functions, right? So the program itself we look at samples later on, has a set of functions that codify the logic that you want to realize to capture the system behavior. Okay. And Yaxim is still available, it still works, you can find it on the net. If not, we will put that in the links for that to our IIT website, which will have this for, right? So again, this is something which we already said, right? It's a discrete event simulation language based on the C programming language. It's a collection of data structures and library of C subroutines that you can link to any program written in C. You can also link that with C++. People have done that, so it's fairly flexible. That's the reason why we are particularly talking about it today. Okay, so we're going to so there are three main entities that when we look at simulation, right, in an Yaxim environment. So there are three objects or simulation objects. One of them is called an activity, and we'll talk about what an activity is later on. Then we have queues or resources, right? So when we are looking at a system, and this is particularly designed for simulating a set of processes that communicate with each other, right? This is more for parallel computing. We have also built networking based simulations with this, and you can build any other form of simulation where you fundamentally require the notion of an event or a process. That's the basic abstraction, and then you also need queues, right? So queues are the servers in the system. So wherever there's a queuing system that you are looking at, we talked about the CPU disk queues that we had earlier on in the course, right? So if you want to model those, then this is a pretty good mechanism to achieve that. Okay, so we have basically activities, queues, and then statistics records. So the behavior of the system is going to be captured with the help of activities and queues, and the statistics records help us obtain mean, throughput, mean, standard deviation, and lots of other histograms and so on. Right, so some of these are built in. You can always extend these the way you want. Okay, and first we look at activities, right? So there are two types of activities. So in a discrete event simulation system, the basic entity is an event, right? The system is described as a sequence of events that happen at different points in time, and so event 1 will take place at time 0, event 2 at time 10, event 3 at time 15, and so on. And as we discussed earlier on, right, the system will simply jump from the first event, which is time 0, the next event say time 10, the next event say time 15, and so on. That's why it's called a discrete event simulation. So event is your basic unit of activity in a given system. So we can write programs using either event based model or a process based model, right? So those of the students who are familiar with the Unix processes, we know how to write multi-threaded systems, right, or multi-process programs where you create a set of processes and the processes can communicate with each other, right? So we use, for example, fork in Unix to create a new process, or if you use a thread library, you can use the corresponding thread create package. Thread create, for example, will create a new thread for you, right? So you can imagine the system as a sequence of events that happen over a period of time, or as a sequence or a set of communicating processes, and each process will have its responsibility for managing some part of the system activity, right? So sometimes you'll find that it's more efficient to write event driven programs. For some applications it's more easy to write process driven programs. So both are possible. and we look at the combinations of these in the examples as we go later on. Okay. So I will just highlight some of the main commands in the system, right. So this is what we said. So there is a process activity and event activity, and queues, there are different kinds of queues. For those of you who have done operating system scores, you know what a semaphore is, what a barrier is, flag is, and so on. These are primarily used when you have parallel processes, right, or thread based processes which have to coordinate. Synchronization you probably have learnt about, right, process synchronization. So semaphore is a basic construct, barriers, flags, condition variables, all these are different types of queue structures. And what we will use in our particular system, since we talked about primarily queues, is this notion of what is called a resource. So resource is nothing but a server which has a queue associated with that. Okay, so these are the three main, and the stat rec is the statistic record that I talked about earlier on. And if you look at the program, just a couple of things about how to invoke the program, you will have to write a function called UserMain, right. So UserMain is your equivalent of the main in a C program. The main in this Yaxim program is defined elsewhere, so we cannot rewrite that main. So we write a function called UserMain, and that is where your code starts executing. So whatever program that you write will start executing from UserMain. So that's a small basic there. Then there are several command line arguments which I am going to skip, that you can essentially go through. And compilation is also very simple, right. There is a file called yaxim.o, which is the object file that contains all the necessary pre-compiled files, and then you simply have your file, which is whatever a.c, b.c, and so on. You can then compile that with yaxim.o, and you will get an executable which is like any other C executable that you can run. Okay, there is another way also to compile which I won't talk about. You can go through the manual and figure it out later. So now we come to write operations with respect to these activities. So we will talk primarily about okay, let's get to creating events and processes. Again, I am skipping many of this, we will look at these only as we need. So let us look at how to create a process. So right, a process, if you look at pthread create or fork, right, in Unix you call fork, that creates a new process, the child process, and the parent process can do something and the child process can do something else. Here it is maybe similar to what you would do in a Windows based system, where you call a function called a new process, right. So this is the basic function that you are going to use for creating a new process. So when you start Yaxim, there is no process in the system, there is just one basic process, right. That is, you can now create additional processes as you need, and then define the functionality for each of those processes with the corresponding function, right. So this is again, so new process is the function that you will call to create a process, and this p name is just the name that is going to be given for the sake of tracking purposes and diagnostic purposes and debugging purposes, and there is a function definition. So the body name is simply the name of a predefined function that you write in some other part of the code. So for example, you can write a process that will simply count from 1 to 10. So you will write a function, say count 1 to 10, and define whatever is going to happen there, right. So this is basically the process logic is defined in this function called body name. Okay, and there is something called a stack size which we will skip for the time being. So basically you need to give a process a name and a function that contains the logic that this process is going to execute. That is the main interface to creating a process. That is then how you will create a new process. So a process will be containing a sequence of C lines, C statements, that is all, right, and that basically represents the logic. Couple of important logic statements which are not available in your traditional, right, numerical computation is, one is called a process delay. So process delay is a special function which when invoked within a process, it will simply delay or suspend the process for a specified amount of time. So I can, for example, say process delay 10, and the system will suspend this process for 10 units of time. That unit of time is very important. It is not your real clock seconds, it is simply the simulation time. So internal to your simulator there is a clock that is running that you are in control of, and this is simply in terms of the simulation time units. That is something very important. Okay, and if you want, you can make this also 0.0, which is a special case which I will skip for now. 0.0 is simply to yield the process to some other processes. Remember, your Yaxim program can have 15 processes running, and you might want to just, and this is running on a single CPU, right. So we are actually emulating the execution of multiple processes on a single CPU. So if you want to give up a CPU and let some other process, which is some other Yaxim process run, this is a way of doing that. So simply to yield, and if there is no other waiting process that is that has to execute, then the control will come back to this particular Yaxim process that you are dealing with. So process delay is useful. When we look at some examples, we will see where that is going to be used. And process sleep is a special case of process delay. It is more like putting this process to sleep but you do not specify how long the sleep is going to be. That will wake up later on based on some condition variable, right. That again we do not have examples in this particular class, but that gives you more flexibility of writing a generic system where, for example, timeout, right. Simple example of using process sleep is you put a process to sleep after sending a packet, and you as soon as the acknowledgement comes back, you will wake up this process and process the acknowledgement, and you never know when this act is going to come back. So that can be done by a special condition variable or some other flag that you can use to wake up this particular process. So that is the process sleep. So the two main activities are creating the process and letting the process go to be delayed or put to sleep. Okay. Process join and priority, all those things are optional, which we won't really look at. If you are writing programs where, if you remember, fork and join, right, you can join to wait for some other process to complete before proceeding. Those are particularly specific to parallel processing kind of parallel computing kind of routines. We can send messages, which again I am going to pass over for now. So that is about the process. Okay. So event is similar to a process. So a process has a body that, or right, a function that can be that is associated with that process, and a process can be a long running process. For example, an arrival process in a simulation program can run for the entire duration of the simulation, right. So it has a much longer lifetime associated. That is the definition of a process. It simply can run. You can kill a process anytime, but in theory a process can run forever. An event is similar to a process. The only major difference is event is instantaneous. It gets created, it gets triggered. As whenever it gets triggered, an event triggers, you take some activity, like interrupt, for example, right. When interrupt is triggered, some action is taken, and then that's it. The trigger is forgotten, right. The event is forgotten. You can reschedule the event if you want to, but event typically happens only once. It happens, the function code associated with the event executes, and that's all. That's the end of the event. It simply dies. Okay. So you will find that events essentially give you less overhead, right. Writing a program as event driven involves less overhead and requires less memory, but on the other hand, the other two would require more memory. Okay. So therefore an event is the other way to create an activity, and the syntax for creating an event is very similar, right. You have the notion of event, right. So new event is a function that will create the event for you, and just like before, there is a name associated for debugging, diagnostic and other purposes, whereas body name, just like in the case of process, there is a logic that is associated. Here is also there will be a function you can define that will handle this particular event, right. This is the event handler that is triggered. So Axiom will take care of calling this particular function when this event takes place. Okay. And there are other flags associated with that, which for now we will simply ignore. So all I can do is I can create an event and I can define the logic that will be executed when this particular event occurs in the system. Okay. And there are again a lot of other functions that is associated with that. Okay. Now, so I create an event, right. Sometimes I want to reschedule this event for some other point in time. So let us say a packet arrival takes place, that is at time t equals 10 seconds. So that is when the event is triggered. So you have scheduled the packet. Now you are going to transmit this packet, and you know that you are going to get acknowledgement back in say 30 seconds, right, or 30 time units of the simulation time. So you want to reschedule the same event to occur at some future point in time. That is just for event rescheduling purposes. You know, like how do you decide? That is part of your logic. The whole purpose of the simulation program writer is to understand the behavior of the system and capture all the behaviors using these events processes, right, paradigms. So if you know that you want the same event to occur at a future point in time, right, it is like a birthday, for example. You know 365 days later the same event has to reoccur again. Therefore you can reschedule this particular event at a future point in time. That is the base case, right. So that is what we all know. I have an event, I can schedule that to happen at some other point in time in the future. There are other more sophisticated things like based on semaphore, right, based on flags and things like that, which I think are not relevant to the examples we were going to look at. That is for more sophisticated things. And this something special is called event reschedule based on a resource availability. So I talked about a resource being a server. So a server has a queue associated with that, and the server is normally a single, so we can have multiple servers also. There is a single server associated that is servicing this given queue. So when I schedule an event to be scheduled with respect to a resource, so this event will go and wait in the server's queue, and when its turn arrives, right, because what will happen is the server will handle all the other packets or other events that is in its queue, and this particular event will be handled whenever it gets to reach the server for getting serviced at that server. It is a little bit confusing now, we will look at the example code now, but that is another function we will see about this event reschedule resource and other things also we will see. Okay, and what I skipped earlier on, there is a general thing called activity schedule resource which is also available, and I am skipping this really fast. Okay, so the same thing can be done. You can also use activity schedule instead of saying event schedule, process schedule and so on. You can simply call a generic thing called activity schedule time. The same function that same functionality as we saw before, where whether it is an event or a process, you can schedule that to happen at some future point in time. Say for example, in this case you are saying that I want this process to be scheduled at 4.5 units in the future. Okay, or you can also schedule this activity based on a resource, which in this particular set of examples it is not there. When we come to our code we will see that. So that is the basics of creating events and creating processes, and now we know that now my Axiom code has a bunch of processes that could be running, each process containing some part of the system logic, right. So for example, I could have an even arrival process, a departure process, a CPU process, a disk process, all those are different processes, each executing some core logic of the system, and between I can throw in a bunch of events that get created, that get deleted as and when it is needed in the system. Okay, so that is these are the two main things. Pretty much most of your code is now taken care of. Okay, and we can create servers by ourselves, right. We can write our notion of a server. We know how to create a linked list, right. A server is basically a queue or a linked list structure, right. It is a FIFO structure or some other more complicated structure that you want to write. So you can create packets or add packets to a queue and service that queue in any order that you want. That is something that we can do ourselves. We all know singly linked list, double linked list, or even a stack and queue, whatever it is that you want to implement it, we can implement. But the Axiom gives you some set of predefined queue structures that saves you that hassle, because maintaining pointers and all those things can always lead to bugs in the system. So we have a special notion of what are called as queues, right. So these are queues are so called resources. Okay, so that is described in this structure called queue. Okay, let's see. Okay, so this is a resource. So a resource in Axiom consists of a set of queue and a set of servers. Okay, and what an activity can do, an event or a process, is to request service time on a particular resource, right. So service time means, okay, I need 4.5 units of service time on this particular resource. If it is CPU, for example, you want to use it for 20 milliseconds. The disk, you want to use it for 500 milliseconds and things like that, right. So whenever an activity makes a request for a resource, if the resource is free, that all that maintenance is done by Axiom itself. If the resource is free, it will immediately service you. If the resource is currently servicing some other activity or some other packet or whatever, then this packet will get simply queued and be picked up for service at a later point in time. So that is implicit queuing is done whenever you simply schedule an activity on a given resource, and then so all that business of queuing, dequeuing, all that is transparently handled by Axiom itself, right. We don't have to see that as to how that is getting done. So let us see how to create a resource. So basically, you will again, like a new event, new process, we have something called a new resource. Okay, so new resource will simply create a resource, okay, and some of the parameters are as before. So the name of the resource, again for diagnostic purposes, what we will use that. Okay, and then the discipline. So queue discipline we are all used to, first in first out, but there are lots of other disciplines, right. Last come first served is there, LCFS is there. So let's look at some of those queuing disciplines. Okay. So first come first served, simply the order of getting into the queue, that is what is that you use for removing the packets from the queue. Last come first served, and then there is last come first served with preemptive resume, which means you can preempt a process, right, and then you can do FCFS with preemptive resume with priorities, right. And same way there are a bunch of processor sharing is something that some of you have done networks course might remember, right. Your GPS comes from this, or you can simply have a basic round robin scheduler. So round robin schedulers, for example, if you put 10 packets in the queue and each packet has got 100 bytes, right, and with round robin you can simply say that from each packet, say 10 bytes is my quantum or time slice as we call that, right. So there is this notion of a slice argument that you have to provide. If you specify round robin, you also have to specify the time quantum that is going to be used for every process that is going to execute on that particular server. Okay, so that is what we specify. So we specify the name, we specify the queuing discipline, and then also the number of servers. We all done MM1, MM3, MM5 and so on, right. So you can specify the number of servers and Axiom will automatically create that many servers, but this is a single queue, right. There are not multiple queues, there is only one queue in the system, and but I can, this is like an MM M system, right, and then slice is basically, in case of round robin alone, we have to specify what is time slices, the basic unit of scheduling quantum is. So you can now create a resource. So we have now seen processes, we have seen events, we have seen resources. That's all that we need. Everything else can come in, right? So even sometime whatever be the schedule, the simulator that you are using, whether it's OpNet or NS2 or OmNet++, ultimately that is what is happening. You create a bunch of logic. Only thing is that logic is organized in terms of set of modules, for example, right? OmNet++ defines it in a modular fashion. NS2 you have, right, various objects that are created, but ultimately underlying what happens is there are events created, event scheduled, and that's it, right? And this happens over and over again, and finally you can stop the simulation at some point in time. Okay, so before the simulation terminates, what do we want to do? We want to measure performance metrics, right? The whole idea of running the simulation is to get some values out of the system. So we need to measure performance metrics, and performance metrics we can do that ourselves, right? And depending on the system, in case of OpNet, you can probably have a whole bunch of performance metrics that you have to go and search and, right, dig up and find out what they are. In the case of NS2, you normally have a trace file, right, that simply dumps everything into a large trace file. Then you have to run a Perl script or awk script to actually figure out, right, what the packets are, what the throughput is, and all sorts of things are done manually. Or in our case, we can choose to dump whatever values. So you keep on aggregating some statistics variables as you go along, and you can just, for example, number of packets, right, completed. You can simply have a counter that is counter, right. Every time a packet is finished, you keep incrementing the counter. At the end of the system, you can say I delivered 10,000 packets in whatever 50,000 time units. Therefore, throughput is 0.5. Right. That is something that we can do. Yaxim provides you a set of basic statistics records, right, which is little bit which helps you in some cases. Mostly we write, you know, other our own statistics routines also. Okay, so for example, you can initiate collection of statistics on a particular queue. Remember the resource we created above. So we can ask Yaxim to keep track of various things, right? The amount of time this server is busy, for example. That's one thing. Utilization of the server, right? Row value that we have defined in MM1 system, for example. You can ask the Yaxim to do that for you, or the service time for these different packets. You may just say calculate the mean service time, or you can also say calculate statistics in terms of histograms, right? So you define what your different number of bins are and what the right values for those bins are, and then it will automatically keep track of those things. So there are, you know, very sophisticated things, so you can do that. And besides the queues alone, right, so you can directly gather statistics for the queues with that queues collect stats, but you can also collect other statistics, for example, number of packets delivered or the delay for a particular packet, right. All those things you can do that with the help of this notion of a statistic record that is predefined in Yaxim. So new statrec is a function that is available, and here you can specify, right, whether it's interval point or interval, and whether you want to, right, it computes the number of samples, maximum value for the samples, minimum value for the samples. So every time you transmit a packet, you will call this new statrec. Automatically it increments the number of samples. It updates the max value, min value, right, and the mean value. All of these things are automatically taken care of, right. So this is a convenient way of doing it. You can also do it in different ways. Okay, and so the function we will call to every time we want to update or add a new value for statistics collection is to call this statrec update function, which we will see examples of as we go along later on. So that is your statistic set of routines. So now we have pretty much everything in place now. So we have the processes, events, the queues, all the statistic stuff. Then only one important thing is remaining, and that is actually running the simulation, right. So we need to actually somehow trigger the simulation. So if you look at the simulation code, right, you will see there is a lot of definitions. Here is a set of processes, here is a set of events. All those get created, but at somewhere you have to give the initial trigger, right. It's like creation. Somebody has to come and start that first event, right, to occur, then the rest of the events will automatically start happening, right. So that first event creation is handled with the help of this special set of functions. We will talk about that. Okay, I am not talking about the random variables for now. So basically this is called a simulation driver, right. So only when the simulation driver starts executing, do all the events get scheduled, all the processes get scheduled, and so on. So until then it's like a static set of definitions and nothing is really happening, right. So this is the main part of the simulator that is actually controlling the sequencing of all these activities that are created in the system. Okay, and the basic function that you would see is driver run. So driver run is the one that will start your simulation to execution to get executed, and you specify the timeline and how long do you want this to be run, right. So we can say 10,000 units. Again, time is important. This is not microseconds, milliseconds. This is simply simulation time units. That is something you have to be aware of. And whenever you are say creating a system which has 100 Mbps links and so on, you have to know how to translate this real time values into simulation time values, and you can again define the granularity of your clock in this particular. It can be, you can say one simulation time unit equals 10 microseconds or 10 milliseconds or 10 seconds, whatever it is you want you can define, and based on that you will advance the clock internally when you create and delete events. So this is the main thing. Once you call driver run, it will keep running until it is interrupted. You can always interrupt the simulation by a separate call called driver interrupt. You can interrupt an existing simulation, right, or it will simply run to this timing, whatever it is, a million units of time, it will simply keep on running until that point in time. So we have seen earlier on, right, most important thing in a simulation is when to stop the simulation, right. So whether is 10,000 units okay, 100,000 units okay, we never really know, unless because each simulation run might converge at a different point in time. So what we do is we have talked about termination conditions, I think in the theory part, right. If you go back and look at the other lectures, you will see we talked about terminating conditions based on the mean values, right. There are lots of different conditions that we have discussed, and trying to find that out is a little bit of a challenge. So mostly people cop out and just specify some large value, right, whatever the guide says you simply follow that. If it says run it for a million units of time, you will run it for a million units of time. You do not want to because it takes 2.5 days to finish that, but that is not an option, right. You prefer about 100 units of time, you get some samples and you are very happy, but remember that unless you collect a large number of samples, you cannot really get statistically significant results. If you run it for 1,000 time units, you might get about 50 samples. That is nowhere near to get some meaningful interpretation of the results. So that is why running it for collection of large number of samples is important. How much time is not so relevant as the number of samples that you are collecting, because if you say sampling for delay, right, you need to know. For example, you are trying to figure out bit error rate, right, in a particular system, or a packet drop rate in a particular system, and if your packet error rate is 10 to the power minus 6, right, you have to run at least a million packet generations or packet completions before you can see the first packet drop. So if you really want to, if you stop at 1000, you will say that packet drop rate is equal to 0, but even 10 power minus 6 you have to run at least 1000 times that. So 10 to the power 9 completions you will have to get to make sure that your packet drop rates are meaningful. So those are also very important conditions, right. And right now, yeah, even most of the time we just select a large enough number, but what we actually do is we run it for increasing numbers. You will run it for a million units, 2 million units, and find that what is the compromise between the time taken, the real time taken for a simulation, and the accuracy of the values, right. If you find that the code is converging reasonably well, then you can stop earlier. So in fact there is extension to Axiom called a new stat rec, which you can actually, there is something called driver auto terminate. I will go through that later on, where you can automatically terminate the simulation once certain convergence conditions are attained. We talked about termination conditions, so those are actually programmed as a separate set of functions. So ideally what you want to do is if you want to say converge on delay, if delay with every 500 samples does not change, the mean delay, right, the mean delay after 9,000 samples and mean delay after 10,000 samples is roughly the same, then you simply want to stop at 9,000 samples, right. So you have special convergence conditions that you can define, assuming that delay converges, right. So then you want to, because you are not just running for one parameter value, you are going to take a parameter value, run that for 30 replications, 10 replications, therefore this simply takes time, and you have several combinations of parameter values. Those who finished their MTech thesis recently will know, right, the number of replications, the amount of time it takes, and those still working on simulations also know, right, in this class at least how long it takes to get a basic result done. It takes days, and then you run 10 times that, so it takes about 25 days for one data value, then you have 100 parameter combinations, so right, it takes forever, and then you need more machines, or you have to be clever to stop your termination as soon as convergence takes place. So that is something that is very important, right. So driver run 10.0, which means that run for 10 units of time. So that is the basic thing that we will see. You can reset the driver in between if you want to, which means we can reset the driver and start it again. So resetting the driver will basically zero down, bring all the statistics records to the original state, and then keep going after that. Okay. So that is these are all the main functions that you require in order to execute a basic simulation. So before I proceed, questions from the class, small though as it is. It's important because, right, when we have to think about the students that are listening outside, and this is right, it's a very basic introduction.
Sir, how does the simulation time that is mentioned in the driver run function translate to the real times?
That is something that you will have to do the translation, right? So you have to define 1 unit of time is equal to say 1 microsecond. So that is something that you will have to figure out, right? So that translation you have to do, and unless we an example we won't be able to do that. So for example, if you say that so let's say I am generating say 30 packets per 30 million packets per second, right? And so correspondingly, let's see how will you do that. So in that case you will have your so you would be generating if you just use second as the basic unit of time, right, then you will packet arrival rate will, or the inter packet arrival time would be 1 over the 30 million packets of time, right. But if you want to say that I am not able to generate this at 1 second intervals, you want to make it something large, you can say I am going to convert this time scale to 1 unit of time is about 10 seconds or so, right. If you decide to do the translation that way, so one simulation time is 10 seconds, then you will translate your corresponding 30 million packets per second to 3 million packets per simulation unit of time, because you are basically condensing your time scale that way, right. So that's why you will have to try to do that, because when we run into systems where we are talking about 1 Gbps links and so on, then what happens is the number of packets that get generated is very large, right, and the time between these packets is also very small, and that leads to large number of events that is getting created and so on. So that is something that you have to decide at what level of abstraction is okay, right. Even though the system says 30 Mbps, if you translate that to 3 million packets per unit time, is that sufficient to give the level of accuracy that you are looking for? That is something that only you will have to figure out after experimenting and seeing if that is okay, and then at the end you will translate that back to.
So this you will have to specify in the code?
Yes, you will have to specify in the code. You specify in your code. So if the user parameters will be in terms of say megabits per second, it is up to you. So say lambda he says is 30 megabits per second. In your code you are saying 1 unit of time is 10 seconds. Then in your system simulation, the lambda will be the original lambda is 30 Mbps, and because you are having it on a more grosser time scale, it will be just 3 million packets per simulation unit of time. So that is something that you will have to program manually at the beginning of your system. Okay, so that is the basic. So now let us look at one program, right? Is it clear enough? No, here it is looking, but I think when the system captures, it's probably better. You want me to zoom? We can zoom. Okay, is that better? Because I want to have the entire screen show up. Okay, yeah. So this is a basic MM1 queue, right? MM1 queue, who have been following this, whoever has followed the lecture so far will know what the MM1 queue is about, right. So you have exponential service time, exponential arrival process, right, or Poisson arrival process, and there is exactly one server in this particular system. So how do we build a model? So we have seen the theoretical results for MM1. We know the delay is 1 over mu minus lambda, right, all those derivations we have seen. How do we validate that? The two ways of validation, one is theoretical results are known, one is validation with the help of simulation, other is with a real system. You can actually build a system, right, where people come and go, where you actually pretend that they have exponential service times and so on. It is easy these days to actually do a simulation based verification. Okay. So this is the definition: packets arrive to the system based on the Poisson arrival process, and when they arrive they are queued at a server, right, and the server has the service time for the packets is exponential, right. So that each packet will have exponential service time, and we are servicing these packets in first come first served mode, right. It is simply FCFS or FIFO as we know that, right. And this system actually terminates based on two properties. One is it will simply run for a maximum unit of time, or we can also converge, which I mentioned earlier on, right. By looking at this replication method, you can converge. At the time of conversion you can start the simulation. We will not look at convergence initially, we will simply look at running the simulation for some large amount of time, that is you specified at the command line. So the basic way to run this code is as follows, right. So this is executable. Minus h is a axiom thing that says don't print some headers, otherwise the axiom prints some useless headers, and the parameters are basically 4 parameters. This is your lambda in your MM1 parlance. So this is 0.5 packets per unit of time, whether it is second or whatever, we do not care. 0.5 packets per time unit. Service rate or departure rate, this is mu, right, this is 1.0 packets per unit time, and this is, if I set this to 1, which means terminate using replication, or if and this last value will be ignored if I set this to 1, or if I simply look at the other way where we use the same thing, right, 0.5 is the arrival rate, 1.5 is the departure rate. If the third parameter is set to 0, which means that simply run this for the specified amount of time in the command line. So this is the basic way that we are going to run the system, and it is of course very easy to extend this to multiple servers, and some of those I think are there. We look at the assignments which I will post later on, the companion assignments will tell you how to vary this basic set of programs. Okay. And initially also this particular implementation can support finite buffers, infinite buffers, and all those variations are possible. Okay. And you can also easily change this. The beauty of simulation is that if I want to replace my exponential service time with some other service time, it is very simple. I just need the corresponding random number generator to be implemented, and if you look at Raj Jain's book, you can there are ways of simulating other kinds of random variables. It is very straightforward. Okay. And likewise arrival process also, right. So that is the sometimes you find that the process of arrival, process of departure is neither Poisson, right, nor exponential. In that case you look for way, you can simply encode whatever that you want, so that gives you a more realistic view of the system, but you always use the corresponding theoretical results for MM1, because MM1 is easier to get theoretical results for. Of course there is GG1, if you look at Raj Jain's book there is, right, G1, GM1, MG1, all those results are available, and you can try to combine. The GG1 is the most generic system, which is harder to find very specific closed formulae solutions, right. So anyway, so this is a basic program. You should in fact try to play around with this, change the basic departure process, arrival process, everything, and then see what kind of system behavior you are observing. Okay. Yeah, and this has been running for a long time. All right. So the only thing that you, when you write a Axiom program, is you need to include the sim.h. This is specified by or supplied by the Axiom library. So sim.h is the only thing you will have to include, and everything else is whatever you want to do. And by default we create a structure cinfo that stores the start time and the finish time for this customers, right. Every time a customer arrives, we need to give the customer ID number, token number. We record the time that the customer arrived and the time that the customer finished. That is what is basically used to store here. Now this arrival process and customer, so these are the functions that are going to be associated with two different activities. So arrival process is going to be associated with the arrival process, even the process we are going to create later on, and customer is simply another logic that is going to be associated with the departure event or departure process. Okay. So this is simply your prototype for two functions, will be defined later on. And by default it will be void, right. This is the way that it will define the correspond. This is a function prototype definition for those functions. Okay. So the global variables, which we actually need not use global variables, but sometimes when you are sharing data between processes, it is easier to use global variables. But you should remember that when you are writing a multi-process simulation and you use global variables, you have to think about synchronization. You would need actually, whenever a single variable is going to be shared between multiple processes, you need semaphores or locks for synchronization purposes, and this probably does not have that, but that is to simplify, otherwise it is too complicated. So anytime say a particular variable is going to be updated by two different processes, you definitely need the corresponding synchronization constructs. In this case arrival rate, departure rate are both just static values, they are not going to be changed, therefore we do not really need that. Okay. So then this resource is again a queue, right. So this is a queue that is going to be, we are going to create this queue and enqueue packets into this particular system. Okay. Customer ID and then stat rec. So we promised that we will use something called stat rec. So this customer delay is a statistic variable or record that is going to keep track of all the packets that are being executed. So every departure process we will record the delay taken by that particular packet or customer in this given variable. So these are the four different variables that are primarily necessary. Okay. So that is the first part of the code definition. Okay. So now let us move on to UserMain. So I mentioned that UserMain is the starting point for a Axiom program, right, because main is already defined somewhere within Axiom, deep in Axiom's definition. Okay. So there are some there are some default values. So max time is what I will normally use for terminating this. That is the number of amount of time that the simulation has to run, and max time we can update based on what we read from the command line. Okay. So arrival process is the process that I am going to create. So that is the definition for that. Okay. So these are just command line arguments as to we are going to read. So the first argument is going to be read into arrival rate, second into departure rate, and so on. And the max time is again A to F. So that is your standard conversion from ASCII to float or integer. Okay. Now this is very important, right. So random init, you need to initialize the random variables, right. Anytime you run a simulation, you have to initialize the random, you have to call this corresponding random initialization, even if you are using srand or srandom and so on, or random for example, you always call srandom to initialize the seed, because when you have multiple runs of the same system, you want to make sure that, right, they are initialized the different seeds, so the randomness in the way packets are generated or the service time is generated does not affect the behavior of the system. You want to make sure that randomness has no significant impact on system behavior. Okay, so that's why this random init is there. There are also other associated functions like select set stream is there. We will not get into that. Okay, so customer delay is the statistic record that we have created. So this is the function call, right. So it's simply this is a name when we use for debugging purposes, diagnostic purposes, that is straightforward. So Q is again my new resource, that new resource function is called. So I am creating a server, and the name of this simply server. Remember, this is the scheduling discipline, the queuing discipline is FCFS. I am creating it with only one server, and the last parameter is not relevant. This is the slice time that we saw earlier. Okay, so that's all. I have a single server running FCFS as the scheduling discipline, done with one single thing. I also collect statistics on this particular queue in terms of the length of the queue. This is E of NQ, right. Remember, we compute that. This is utilization. What is the fraction of time the server is actually being utilized? In MM1 we say rho equals lambda by mu, but that is definition. I would actually want to measure the utilization. How often is the server being utilized? You measure that and you record that, right. That is what this is, to validate whether utilization actually equals lambda by mu. Okay, that is what this is for. Okay, and then so this is your basic. Now the server has been created, this one particular, right, statistical record has been created. Now we come to the main part of the code. The main part of the code is creating the arrival process. So remember, we saw arrival process. So this is the name of the process, and this is the function that contains the logic for this particular process. So now this again is only a definition. If I simply leave this program saying arrival process is a new process, that will simply create a data structure called arrival process, but you have to also schedule that, right. Unless it is scheduled, it is not going to get executed. So scheduling is important. So that is your activity schedule time, which simply says takes the arrival process pointer, and then 0.0 means that this is going to start right away, right, which means schedule this process to start running right away. Independent is a parameter which we will skip for now. So all that we say is I have created a process which will start running straight away. So then what will happen, system simulator will create an event at time 0.0, which will or event or a process, with the process will be created to start executing at time 0.0, and that will in turn run the code that is given in this particular function arrival process. Okay, let us ignore this if replicate method for the time being, and then so now that I have created all that I wanted, so now all the objects are in place. Now the important thing is to get the simulation going, and that is driver run. So driver run max time, right, and this max time, if I want to change it from the default value, we did that with the help of our, I can specify max time as a command line argument, and if so, it will simply change that as needed. Okay, so that is, so now what happens is, now if you look at the code, this is it, right. I have created objects, I have created the process, I have driver run max time. So what happens after driver run, when it returns, it means that the simulation is finished. Okay, it is not very obvious, but that is what is happening. Okay, so at the end of driver run, when driver run returns, it means that simulation is run for max time units. Then what do? We want to print out all the statistics that you have collected so far, right. So I simply call statrec report, right, for this Q1, because it has already been collected. I do a statrec report on the utilization, on the length, on customer delay, and so on. Now this is not needed for every simulation. I am using this to show how we can actually invoke these particular things. Okay, and then we then look at, so then finally what do we print? So I am looking at this customer delay, right. There is a default function called statrec mean customer delay. This will now automatically compute the mean for you. So you do not have to go figuring out what the mean value is and so on. As long as we have done the corresponding updates correctly, this is what is going to happen. Likewise, we can also, and we try to do comparison between what theory gives us. This is what does theory say? Theory says MM1 departure delay is simply 1 over mu minus lambda, departure minus arrival rate, right. So we are comparing what the simulation gives us to the value that is given by theoretical formula. That is the first statement. Here this is E of t, the delay value. I can also measure E of n, right, average number of customers in the system also can be measured, and what is that? And that is 1 over, sorry, this is simply lambda divided by mu minus lambda, right, Little's formula if you remember. lambda into delay gives you the number of customers, and I can also get the number of customers from the simulation by using the statrec mean value, right, which says this is length, right. So I'm looking at the length of the queue. So what is the number of packets queued in that particular queue over a time average, right. So at every point, let's say every 0.01 units of time, I look at the length and record that. Then I look at the time averaged value for length, that is my E of n value, right. So this is E of n from the simulation, this is E of n from your theoretical studies, right, that what we derived in class earlier on. So this is what we, so this is a way to compare theory to practice, right. So what does simulation give you? Does it give you what you are looking for? Okay. So now let us look at what arrival process is going to do. So arrival process is simple process. It's basically an endless loop, right. So the arrival process is a process, its job is to keep on generating packets forever until the simulation terminates. Okay. So what we do is we can create the first process right away, but we have this special notion of process delay. Remember we talked about process delay. So what I do is I can delay the process. How long do I want to delay the process? I want to delay the process until the next arrival time. So the inter-arrival time for a Poisson process is distributed exponentially. We know that from our theory, right? And so if the arrival rate is lambda, the departure, sorry, the inter-arrival time is exponentially distributed with parameter 1 over lambda. That is again something that we have covered in class, right. So therefore I want to delay the process, arrival process, by for a random amount of time, and the randomness is defined by this exponential variable with parameter 1 over lambda. So which means that for that period of time, let us say this is 0.02 seconds, nothing is happening, there is no packet generated. So then actually now I am creating a packet, and the packet creation is again an event. So now I am using this event example here, right. So event is I am creating, that is a customer, and I am associating this customer function to be executed whenever this event finishes. Okay, we will see how that is done, and I am filling in all the information, the customer ID I am filling it, and the start time. So getSim time is a function that is defined in Yaxim that tells you the current simulation time, not current real time, this is current simulation time. This is where, this is the time that this packet was created, that is what we are recording here. Okay. And then we ActivitySchedule, I am going to skip that statement. It is simply to associate this data structure with this particular event, so that later on I want to retrieve this event, all that is stored in some convenient place. So simply this will store this C info as part of the data structure that is associated with this event. Okay. So now the event has been created. So a packet or customer has arrived, and the event is now getting created, has been created. Now what is the next thing to do is to schedule this event, right. Where do I schedule the event? I schedule this event to get service on that server that I created, Q1 that I created, right. So the service time for this particular packet is again exponential by our definition, and we saw that if the departure rate is mu, right. So it is 1 over mu is the parameter that is passed to this exponential variable. So now the service time is also going to be automatically exponentially generated. So now I know what the service time is. So now I activity schedule this. So I schedule this event, right, to run on Q1 with service time, which is the basically length of the packet or time of service for the customer. That is what the service time is. Okay. So I have created this particular customer, I have now scheduled this particular customer. Now when, so this is if this the Q1 is empty, what happens? This particular customer will get serviced right away. Okay. And when the customer finishes service, okay, at the time after the service time for the particular customer is over, this customer function, right, that we defined here is going to get called. Okay, that is the basic idea. So as soon as this packet is finishing service, at the end of finishing of service, this event will actually take place. So I am creating an event, it does not take place right away, I am simply putting it in the queue of the server. When the server selects this event or this packet for service, and after finishing service for this packet, at that time this event is set to actually occur. Okay, that is the way, that is how this Yaxim definition is. So at the time of occurrence of that event, you call the corresponding event handler, which is defined in this function called customer. So this customer function will contain all the things needed for recording the departure of a particular customer, right. All our statistics are computed when a customer leaves the system, right. Enters, we are simply storing the start time, departs, we do a whole bunch of other things. Okay. So this is the basic logic that is present in this arrival process, and then this goes on. So what happens after this customer is generated? When is the next customer going to get generated? Again based on this random inter-arrival time, and that is, so this is the loop that we have, right. Every inter-arrival time is basically exponentially distributed. So you will have these packets appearing in the system at periodic points in time, they all get queued in the server, and then that is all that we try to do. Okay. So then what is a customer? Customer thing is very simple. In the info data structure that is associated with this particular event, I store the finish time, which is basically the time that this packet is actually finished service, that is given by getSim_time. So again, this is something you have to imagine, right? This is not a sequential program. These are all things happening at different points in time, right? At some future point in time, this packet has finished service. Therefore, the getSim_time will be the time when this packet has finished its current service, right? And then we simply update the customer delay static update with info finish time minus info start time. That's all. This wait again ignore. There are more complicated ways of computing. It simply says the sample value for this new sample value is info finish time minus info start time. The customer event terminates, customer leaves the system. Now automatically this thing is dequeued from the server. All those things we don't have to worry about. The packet has arrived, packet has been queued, packet has been serviced, and we have only captured the departure statistics in this particular system. Okay, so that is what that's all that this main part of the code is.